Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The Distinguished Lecture Series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome. It's a great pleasure to introduce Samit Dasgupta and Mahesh Kakde for this distinguished lecture series talk today. They are both invited speakers at the upcoming International Congress of Mathematicians in St. Petersburg, and they will be giving us an account of their recent, very exciting, deep work on Hilbert's 12th problem. So, in the year 1900, the mathematician David Hilbert, he announced a list of 23 significant unsolved problems that he hoped would endure and inspire. And even today, that's more than 100 years later, many of these questions are leading to advances at the frontier of mathematical development. The way Hilbert stated his 12th problem, which is the theme underlying Samit and Mahesh's talk today, goes as follows. This is how he said it. The theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. Since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. Finally, the extension of Kronecker's theorem to the case that in place of the realm of rational numbers or of imaginary quadratic field, any algebraic field whatever is laid down as realm of rationality seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. Now, that was Hilbert in 1900. So the fundamental theorem of Galois theory, it sets up a correspondence between field extensions on the one hand and their Galois groups on the other. And even when the Galois group is abelian, there are deep questions that abound. So all quadratic extensions obtained by adjoining the roots of a quadratic polynomial, they are indeed abelian, and their study was commenced by Gauss. Another type of abelian extension of the rational numbers is given by adjoining nth roots of unity of 1. This gives rise to the cyclotomic fields. And Gauss had shown already that quadratic fields are contained in a larger cyclotomic field. The Kronecker-Weber theorem shows that any finite abelian extension of Q is contained in a cyclotomic field. So the point of Hilbert's question is that it addresses the situation of more general algebraic number fields K. What kind of algebraic numbers do we need to construct all abelian extensions of K? This deep and exciting work of Mahesh and Samit will address exactly this problem. All yours, Mahesh and Samit.
Hello. Welcome to this talk on Brumer-Stark units and Hilbert's 12th problem. Um, so I'm giving this jointly with Samit. I'll give the first half of the talk where I'll describe Brumer-Stark conjecture and a Brumer-Stark unit, and in the second half Samit will talk about explicit formulae for Brumer-Stark units and a little bit about the proof of all the statements that I'll give here. So I want to thank the organizers for giving me a chance to speak in this distinguished lecture series. It's a real honor. So I'll start with what number theory is mostly concerned with. So it's about solving Diophantine equations. What this means is you're given a polynomial in several variables with coefficients in integers. And you ask yourself if there are solutions. If there are, then how many there are and how do you find them all? Okay, so this is one of the main objectives of number theory. Here are some examples of Diophantine equations, very famous one. The first one is the so-called Fermat's 2 square theorem. So Fermat asked which primes can be written as sum of 2 squares, and he proved that p can be written as sum of 2 squares if and only if p is 2 or p is congruent to 1 mod 4. The second one is of course the favorite of number theorists. So for n equal to 2, this is Pythagorean, this gives Pythagorean triplets, and for n bigger than or equal to 3, this is the Fermat equation, which we now know has no non-trivial solutions. Okay, so study of these Diophantine equation often leads one to study algebraic extensions of rational numbers. Okay, so for example, Dedekind proved 2 square theorem using Gaussian integers. Okay, so he proved that p an odd prime p splits in Gaussian numbers qi if and only if p is congruent to 1 mod 4, and that gives the 2 square theorem. The study of Fermat equation led Kummer to study cyclotomic fields, and much of what I'm going to say today has its origins in the work of Kummer, for example. Okay. All right. So a number theorist is naturally led to the study of algebraic extensions of rational numbers. In particular, we would like to describe algebraic extensions of rational numbers or algebraic extensions of any number field. Okay, so the first class of extensions to study are abelian extensions, and we have realized that these are hard enough. So let's study abelian extensions. So these are Galois extensions with Galois group, which is abelian. Okay, so Galois extensions with abelian Galois group. All right. So one of the great achievements in algebraic number theory in the early 20th century was class field theory. So this describes abelian extensions of number fields in terms of data that's intrinsic to number field. Okay, but class field theory, as we know it, is not explicit. I'll say what I mean by explicit through a couple of examples. The first one is the Kronecker-Weber theorem. So this is a 19th century theorem which gives an explicit description of finite abelian extensions of rational numbers. So the theorem says that if K is a finite abelian extension of rational numbers, then it is contained in this field Q zeta n that we saw on the previous slide. Okay. So K is given in terms of roots of unity. Another way of saying this is abelian extensions of rational numbers are explicitly generated by some analytic functions evaluated at rational numbers. The analytic function in this case is e to the power 2 pi I x. Okay. The second example of explicit class field theory is abelian extensions of imaginary quadratic fields. So again, this is something that started in 19th century. To describe abelian extensions of imaginary quadratic fields, we need elliptic curves. So E is an elliptic curve. OF here is the ring of integers of this number field F, and E has complex multiplication by OF. Okay, so the group of automorphisms of E is precisely OF. Then Kronecker, Weber, Takagi, Hase, their work sort of put together proves that the maximal abelian extension of F ab, is generated by these two analytic functions. Okay, so the first one is the J invariant or the singular moduli. This is the unique weight 0 modular form on the upper half plane. It has a pole at the cusp. Okay, it's explicitly given by this Q expansion, and W here is the Weber function. So I'll come to that in a minute. So tau here is related to E in a way. So E is given by the quotient of complex numbers by a lattice, and the lattice, you can choose the lattice to have generator 1 and tau. So that's the tau here. So that's how you pass from E to tau. En here are n torsion points on the elliptic curve, and W is the Weber function, as I just said. So this is x coordinate of the points, but it's normalized in a specific way. Okay. All right. So Hilbert's 12th problem asks for such explicit descriptions of abelian extensions of any number field. Okay, so Hilbert says that asks for explicit descriptions of abelian extensions beyond rational numbers and beyond imaginary quadratic fields. Okay. So Hilbert's 12th problem is also known as explicit class field theory, and today I'm going to today we are going to see about a p-adic solution to this. Okay. So all right. So let me start with another classical result, so another 19th century result, which is called Stickelberger's theorem. Okay. So this also concerns abelian extensions of rational numbers. So H is the cyclotomic field. So for simplicity, I'm taking H to be Q zeta n, but it can be any abelian extension of Q, which is not totally real. And I put G for the Galois group of H over Q. So this Galois group is isomorphic to Z mod NZ cross, so units in Z mod NZ, but there is an explicit isomorphism in fact. Okay, so explicit canonical isomorphism. So A in Z mod NZ cross goes to automorphism of H, which I denote by sigma A. And what does sigma A do to zeta n? It sends it to zeta n to the eighth power of zeta n. Okay, so this determines what the automorphism of H is. Okay, so to describe Stickelberger's theorem, I have two kinds of object. First is the ideal class group, and second will be what is called Stickelberger element. So I'll come to that in a minute. So Stickelberger, so ideal class group is an important invariant of the number field. So it's given by, you take all the non-zero ideals of OH. OH is the ring of integers of H, and you mod out by all the non-zero principal ideals of OH. Okay, so for geometers, these are like divisors modulo divisors coming from functions. So this is like Picard group. Okay. Um, a fundamental fact in algebraic number theory is that the ideal class group is a finite abelian group. Okay, so it's clear that it's abelian, but it's also finite. Okay, and it's also a module over Galois group of H over Q. Okay, so we want to study this ideal class group as a module over this Galois group. So one way to do this is through the Stickelberger element. So it's explicitly given like this. So here curly bracket x means the fractional part of a over n. I should have defined this somewhere, but curly bracket of a over n, curly bracket x means fractional part of x. Okay, so the unique number between 0 and 1, so that x minus curly x is an integer. Okay, so this is an explicit element in QG, the group ring over rational numbers, and it has this very nice property that if you evaluate it at any character of the Galois group G, then you get an L value. So I'll describe these L values more generally later. I'll define these L values more generally later. Okay, so what does Stickelberger's theorem say? It says that if you take a multiple of this theta, which actually has integer coefficients rather than just rational coefficients, then that multiple annihilates the ideal class group. Okay, so this is saying something about the ideal class group as a module over this Galois group. Okay, so for example, 2 times n times theta clearly lands inside ZG, and it's saying that annihilates the class group. Okay, so it's in the annihilator ideal of the class group. Okay, so I'll very briefly say how the proof proceeds. Well, we have to, if we take a non-zero ideal A in H, we have to show that A to the 2n theta is principal, for example. And because any ideal in a Dedekind domain is product of prime ideals, any non-zero ideals is a product of prime ideals, it's enough to do this for prime ideals. And for simplicity, I'll just assume that this prime ideal has the property that its residue characteristic is actually 1 mod n. Okay. Then I take this isomorphism between Galois group of Q zeta p over Q and z mod p z cross that I described earlier, and I take chi to be this particular power of this omega. Then I have these Gauss sums, which is defined in this particular way. So summation chi a zeta p to the a. Okay, so this lies in q zeta sub np. Okay, and what Stickelberger proved is he actually found a factorization of a power of this Gauss sum. Okay, so he showed that, first of all, he showed that this power actually lands in q zeta n, and if you take the ideal generated by Gauss sum to the 2n, it has this particular factorization. Okay, and so because p to the n is principal, it means that this 2n theta actually annihilates the class of this math frac p inside the ideal class group. Okay, so what I want us to take away from this is that the Stickelberger's theorem is proven using factorization of these special elements, these Gauss sums. Okay, yeah. So just a remark here that Gauss sums also generate abelian extensions of Q. Okay, this shouldn't be surprising because these are, after all, linear combinations of roots of unity, and we saw that roots of unity generate abelian extensions. Yes. Okay. Yeah, there's a typo here. This should be zeta n to the a, not zeta p to the a. Sorry about this. All right. So okay, so we want we seek an analog of Stickelberger's theorem for other number fields. Okay, so we are going to restrict to totally real fields because that's where we understand and we can do something. um, and so here is the setup. F is a totally real number field, which means that if I take embeddings of F into complex numbers, they all land inside real numbers. H is a finite abelian CM extension of F. So CM extension means a totally complex extension, such that a totally complex extension which is a quadratic extension of a totally real field. Okay, so that totally real field need not be F here. Okay, so that's the definition of CM extension. And I need another piece of notation. So S is the set of all primes of F that ramify in H, and all the infinite primes. Okay, all the Archimedean primes. All right. Furthermore, I need a prime Q, mathfrak Q of F, which is not in S, and it has large enough norm. Okay, it has large enough norm. All right. So then I can define the this is called S depleted Q smooth L function. So earlier I had L sub S without this Q, and if I don't have this Q, I don't have this factor at the beginning. So this is what it means. In any case, so this product is the usual Euler product that defines L functions, except I'm not taking any Euler factors at primes in S. So this is still an infinite product, but I'm leaving out finitely many of these Euler factors, and this is some modification that will make everything integral. Okay, so a priori this makes sense only for real part of S bigger than 1, and as usual this has analytic continuation to complex numbers. Okay, so this is the usual story with these L functions. So the Stickelberger element over rational numbers was a very explicit, had a very explicit expression. Now we don't have that. What we do have is some element in the group ring that can be defined using L values. And so this is what we do. We define an element in the group ring CG, so complex numbers with a priori with coefficients in complex numbers, which is related to L values in this way. So this is for all characters chi of G. Okay. Now a priori, as I said, this is an element in CG, so over complex numbers, but it's a deep theorem of Ziegel, Shintani, Deligne-Ribet, Cassel-Nogues, that this element actually has coefficients in Z. Okay, so Ziegel and Shintani proved that this has coefficients in Q, and with this decoration of with Q, Deligne-Ribet and Cassel-Nogues proved that it actually has coefficients in Z. Okay, so this is our Stickelberger element, which doesn't have any explicit expression, just relation with L values. Okay. On the other side, we had a class group. Now I'm taking a slightly bigger group. This is the narrow class group of conductor Q, and its explicit definition is you take all the non-zero ideals co-prime to Q and mod it out by principal ideals, which are which have a generator which is 1 mod Q. Okay, so this is this surjects on the class group of H. So this time I'm taking something bigger, and if I can annihilate this, then of course I'll annihilate the class group. Okay. So as an analog of Stickelberger's theorem, Brumer made the following conjecture, and which is that theta actually belongs to the annihilator ideal of this Q smooth class group. Stark made a different conjecture which turns out to be equivalent, and this was studied by Tate, and he kind of made everything precise and studied the relationship between what Brumer had done and between what Stark had done. So So let me call this Brumer-Stark Tate conjecture, which says that this theta actually annihilates this class group. Okay, so our first theorem is that the Brumer-Stark Tate conjecture holds up to two primary part. Well, what do I mean? I mean that um, that if I invert 2, then this theta indeed annihilates the class group. So I have to stay away from the two primary part of the class group. So 2 is always is a difficult prime in number theory, and in fact there are some conceptual difficulties in handling 2. It's not just a technical thing. So this is a work in progress, but we haven't done it yet. Okay, so this is the analog of the classical Stickelberger theorem. Now one would kind of try to do this by looking for analogues of Gauss sum. So you would I mean, if we were to follow Stickelberger, then you would look for analogues of Gauss sum, look at its factorization, and then prove this annihilation statement. Unfortunately, that's not that is not how it works. We don't have a priori, we don't have analogues of Gauss sums. Okay, so the way we work is we prove this conjecture directly, we prove this annihilation statement directly, and then using this annihilation statement we obtain analogues of Gauss sum. So if you know that P, the class of P is annihilated by this Stickelberger element in this class group, then you know that P to the theta is principal. So you can choose a generator which is congruent to 1 mod Q, and because of our condition on Q, this generator will be unique, and this turns out to be the analog of Gauss sum. Okay. So in general, the strategy kind of goes the other way around. You first prove the annihilation statement, and as a consequence you get something like a Gauss sum. Okay, and Samit made a remarkable conjecture which actually gives a explicit p-adic analytic formula for these Gauss sum. So now we have existence of this Gauss sum, and we have an explicit p-adic analytic formula for this, which is also our theorem away from p equal to 2. Okay. Alright, so let's move on and study some refinements of the Brumer-Stark Tate conjecture. And the reason I'm going into these refinements is because these refinements are essential for our method. Okay. So first refinement is the so-called strong Brumer-Stark conjecture, which says that this theta doesn't just, I mean, this is slight modification of theta, doesn't just live in the annihilator ideal, but it lives in what is called the fitting ideal. But we have to take several modification here. So this is what I mean. A hash is a map on ZG, which is a Z linear map, which on the group elements is given by G going to G inverse. Okay, so that's what this theta hash is. The minus here simply means we take the minus part. Okay, yeah, this I have to invert 2 here, sorry, this is yeah, another thing I missed. I have to invert 2, so m minus is m tensored z1 over 2g, z1 over 2g mod 1 plus the complex conjugation. The m check here is the Pontryagin dual of m. So the fitting ideal of the class group is much harder to describe, but there's a recent work of 2 Japanese mathematicians, Kataoka and Atsuta, who describe the fitting ideal of the class group itself. But here we describe fitting, here the conjecture is about the fitting ideal of the dual Pontryagin dual, and we have to take the minus part. Okay, All right. So, and I forgot to write the to invert 2 here, but everything is with 2 inverted, and so the second theorem that I'm going to state is that uh,
Recording in progress.
sorry for the interruption. So I just made the correction. So I'm inverting 2 here, and the theorem we prove is that this conjecture of Kurihara is actually true. Okay, so this is our second theorem. Um,
Recording in progress.
Okay, so our third theorem and the final refinement of the um, of Brumer-Stark conjecture is this remarkable conjecture made by Burns, Kurihara, and Sano. So they define some Selmer group. So this is a subgroup of the first cohomology group. I'm not going to define this at all. So they define some arithmetic object that actually has a principal fitting ideal, and it's generated by this theta hash. Okay, so this is quite remarkable, and it's actual equality rather than an inclusion. And as I'm going to tell you in a minute, this is essential for us, that this is an actual equality. Okay, so yeah, these refinements are indispensable for our method. Okay, so how do we go from these refinements to the conjecture that we are interested in, the Brumer-Stark Tate conjecture? Well, let's first go from the Burns Kurihara Sano conjecture to Kurihara's conjecture. So there's actually a surjection from the Selmer group to the Pontryagin dual of the class group. The class group that we had, and when there is a surjection like this, you get that the fitting ideals are actually the fitting ideal of the bigger thing is contained in the fitting ideal of the smaller thing. So if we show that theta hash belongs to the fitting ideal of the Selmer group, we get that theta hash belongs to the fitting ideal of the class group. And then how do we go from Kurihara's conjecture to Brumer-Stark Tate conjecture? Well, it comes from these 3 observations. First is that the fitting ideal is a stronger invariant than the annihilator ideal. So the fitting ideal of the dual class group is contained in the annihilator ideal. And because the ideal class group is a finite group, so annihilator of Pontryagin dual is actually, you take the annihilator of the class group and apply this hash map to it. That's all there is, and we just use that the class group is finite. This has nothing specific about class group. It's just the fact that class group is finite. And then the third observation is that, well, these refinements are only about the minus part, but that's okay because this theta actually lives on the minus side, which means that chi of theta is non-zero if and only if chi is totally odd. Okay. Yeah. All right. So so that's how one goes from these refinements to the conjecture that we are interested in, which is the conjecture about the annihilator of the class group. Okay. So I'm going to end with the first reduction steps, and which makes precise why we need these refinements. So we want to prove this equality, but it's enough to prove one inclusion. Okay, this is sort of a classical observation in these sort of conjectures in Iwasawa theory. So if you have some class number kind of formula, then you can prove one inclusion. Okay, but in this particular case, it's kind of tricky, but nevertheless it works. So you need to prove one inclusion. One caveat of this is not, you can't just prove one inclusion for one extension H over F. You have to prove it for all possible extensions, and then you bootstrap to actually get an equality. Okay, and so we use Ribet's method to actually prove inclusion in this direction. So we prove that that the fitting ideal is contained in the ideal generated by theta. So this is the inclusion we prove, and the strange thing about this is that this actually is an inclusion in the reverse direction than what we are interested in, the Brumer-Stark Tate conjecture. So this is why it's necessary that we have an equality here, and this is why it's necessary that we have all these refinements. Otherwise, Ribet's method will never give you what you want if this was not an equality. Okay, so I'll stop here. Thank you.
Hello. So this is the second half of my lecture series with Mahesh. I want to thank Mahesh very much for the first half, and thank the organizers very much for inviting us to give this lecture series. And I'm very much looking forward to the live question and answer session, interactive session that we're going to have in a couple weeks. So we're discussing Brumer-Stark units and Hilbert's 12th problem. So let me kind of go back and give some motivation that was already given by Mahesh. It's going to be the focus of my talk, which is this question of explicit generation of class fields. So to set this up, we let F be a number field, which is just a finite extension of Q. And we would like to understand the maximal abelian extension, which I denote FAB, and this was defined by Mahesh. This is the compositum of all finite Galois extensions of F whose Galois groups are abelian. If you put them all together, you get something called the maximal abelian extension, and it's denoted FAB. And the construction of this extension is known classically, you can say, for F equals Q by the Kronecker-Weber theorem, which says that the cyclotomic extensions give you the maximal abelian extension. And for a quadratic imaginary field, so this is Q adjoin root negative D, where D is a positive integer that is not a square, then you obtain the maximal abelian extension as the special values of some modular functions, as Mahesh explained. And so Hilbert, in his 12th problem, asked for the generation of this maximal abelian extension FAB using the special values of transformation properties of complex analytic functions. Okay, so what we're going to be doing is going to be using a p-adic construction, using some p-adic integration. So this is probably not a solution to the question of explicit class field theory that Hilbert would have been very happy with, but it is sort of a solution to the same problem that he was interested in, which is how do you generate the maximum abelian extension of F using information that's intrinsic only to F? So sort of without already giving yourself the answer, how do you generate the extension? And so class field theory is a very good first step towards this, because class field theory, while it does not describe the field FAB, it does describe the Galois group of FAB over F. And more precisely, it kind of gives an enumeration of some finite extensions of F whose compositum or whose union is all of FAB. And it kind of describes what the Galois groups of these finite extensions over F are. So let me describe this a little bit. So this is a little review of some of the basic statements of class field theory. And for every positive integer n, there is a field extension, which I'll just denote Fn of F, that's called the narrow array class field of conductor n. Okay, and these have some nice compatibility properties. So Fn is contained in Fm if n divides m. FAB is the union of all of them. So these kind of, if you understand these finite extensions Fn, you kind of understand all of FAB, because FAB is just obtained by putting them all together. And we know exactly when Fn is contained in FAB. And furthermore, class field theory tells you the Galois group of Fn over F. So we saw these class groups in Mahesh's lecture, and in general, we get generalized class groups. Okay, so I won't tell you exactly what these are, but I'll just tell you that for F1, this is called the narrow Hilbert class field. You get the narrow class group, which I've written in a more algebra geometric way as the narrow Picard group of the ring of integers of F. And what's maybe even easier to describe is the Galois group of Fn over F1, right? So you can just say what the Galois group of Fn over F is. That's a generalized version of this narrow Picard group. It's a generalized class group, but it's actually easier to say what the Galois group of Fn over F1 is. Okay, so this is sort of some subgroup of that generalized class group, and it's the Galois group is O mod n star. So you take O and you mod out by the ideal generated by the integer n, and you take the units of that ring, and then you mod out by the totally positive units of O. Okay, and here O is the ring of integers of F, which I should probably define. It's done below the line. So this O is the set of elements of F that are roots of monic polynomials with integer coefficients, right? So in the case when your number field F is Q, this O is just Z. And in that case, this Qn, the narrow Ray class field of conductor n, is just the nth cyclotomic field, Q adjoined zeta n. So Q adjoined e to the 2 pi I over n. And the Galois group of this Qn over Q, if you look at the formula above, it should be Z mod n Z star modulo the totally positive units of Z. But of course, Z only has 2 units, plus or minus 1. The positive unit is just 1. So you're really not modding out by anything. You're just modding out by the identity, which is to do nothing. So you get Z mod n Z star as the Galois group of Qn over Q, which is a sort of a classical, fact from introductory Galois theory. Okay, so so this is kind of the prototype that we want to mimic, telling us what is Qn actually equal to. So class field theory doesn't tell you what Fn actually is equal to, but it just tells you that there exists some field with some nice properties. Okay, and in the case of Q, we actually know what the field is. It's Q adjoined zeta n. All right. So the question of explicit class field theory is to go beyond what I just told you, right? So class field theory describes the Galois group, right? The Galois group of F ab over F is the inverse limit of the Galois groups of Fn over F, which I kind of alluded to as generalized class groups, and there's a precise formula for what they are. So you take their inverse limit and you get the Galois group of F ab over F. But the goal of explicit class field theory is to construct the field F ab itself, not just its Galois group, okay? Or equivalently, each of the fields Fn. And one wants to do this using analytic functions depending only on the ground field F. So as Mahesh said in his lecture, an example is this Q ab, which we know is by the Kronecker-Weber theorem is generated by the nth roots of unity. So you can view that as the special values of this one analytic function, e to the 2 pi ix, and you just evaluate that one analytic function at certain special points. And in fact, the special points in this case are exactly the field itself, Q. All right, so you evaluate this analytic function at the points of the field and you get the maximal abelian extension. And this is kind of the framework that Hilbert had in mind, that you have these complex analytic functions, that kind of made sense to evaluate at points of the field. And if you plugged in the points of the field, you would get the maximal abelian extension. So unfortunately, our solution to telling you what this F-ab is, which we will tell you later in this talk, does not proceed in that way with these complex analytic functions. We use some p-adic integration instead. Okay. So now our approach is through the Brumer-Stark conjectures, and I want to also introduce this Gross-Stark conjecture, which I won't say anything very specific about, but just describe in qualitative terms. So Gross gave a refinement of the Brumer-Stark conjecture, which is called the Gross-Stark conjecture. So the setting for this is that of a totally real number field, which is a field such that every embedding into the complex numbers is image contained in R. So for example, Q adjoin a positive square root, such as the positives. So the square root, of a positive number, such as the square root of 2, right? Any embedding of Q adjoin root 2 into the complex numbers takes the root 2 and sends it to either positive root 2 or negative root 2. So it lands in the real numbers either way. So Q adjoin root 2 is a totally real field. And for such a totally real field, the Brumer-Stark conjecture predicts the existence of certain elements in these extension fields Fn, which are called Brumer-Stark units, and they're related to L functions in a very specific way, as described by Mahesh in his lecture, using this sort of the valuation at primes above P of these units should be related to special values of L functions. Now, the Gross-Stark conjecture, I won't say much about it, just that it's a refinement which relates these units, the norms of the p-adic logarithms of the norms of these units, to p-adic L functions of F in a very concrete way. So it's a refinement to the Brumer-Stark conjecture. So Gross-Stark says, yes, these units should exist, satisfying Brumer's equation in terms of relating the valuations to classical L functions. And furthermore, those same units should have the property that their p-adic logarithms are related to p-adic L functions. So it's a refinement to the Brumer-Stark conjecture. And I want to put up a picture of some of the mathematicians that Mahesh mentioned in his lecture. So Stickelberger, who in 1890 proved this theorem on the factorization of Gauss sums which laid the groundwork for Brumer to state his generalization for arbitrary totally real fields. So we don't have the analog of Gauss sums in this setting, but Brumer's conjecture is that there should exist units or p units that satisfy the same properties that Stickelberger's Gauss sums satisfied in terms of factorization. Now, Stark was writing down in the 70s very similar conjectures for rather than p-adic places, Archimedean places. So he was looking at Archimedean absolute values rather than p-adic absolute values and relating those to derivatives of L functions. It's a more transcendental kind of conjecture. And Tate kind of realized that these were the same conjecture. That is, if you replaced in Stark's conjectures the infinite place with the finite prime, then you obtain Brumer's conjecture. And in some sense, Stark's conjecture was a little bit finer because he had some additional conditions that the units had to satisfy. And Tate realized that those conditions should be satisfied in Brumer's setting as well. And so by combining this idea of Stark with that of Brumer, we get the Brumer-Stark or Brumer-Stark-Tate conjecture. Okay, so before discussing my work with Mahesh, I want to discuss some of my prior work in this area. So, way back in my PhD thesis, I stated a conjectural exact formula for Brumer-Stark units. So this is a further refinement of not just the Brumer-Stark conjecture, but of Gross's conjecture. So this was, not just saying what the log of the norm of the unit should be, but just what is the unit on the nose. And that's a conjecture I want to focus on a little bit in this talk. After my thesis, I generalized the context of this conjecture and work with Pierre Charlevoix and Matt Greenberg and Michael Spiess to the sort of arbitrary setting of arbitrary totally real fields. And Darmon was my one of my advisors and formerly my advisor. I was a student at Berkeley. Darmon was at McGill, and so we sort of wrote a joint paper on this back during my PhD thesis on the case of real quadratic fields, which is what I was interested in at the time. Okay, so and then later on, joined with Darmon and Pollack in the first paper, and then with Mahesh and Kevin Ventullo in the second paper, we proved the Gross-Stark conjecture. Okay, and here's a picture of Gross at top. Okay, and so the new results that Mahesh has already stated in his lecture are these two theorems. The first is that the Brumer-Stark conjecture holds basically away from 2. 2 is a troublesome prime. And as Mahesh mentioned, we're working on this case and it's quite difficult. And the second theorem is that my conjectural exact formula for Brumer-Stark units holds. And again, there's some caveats here that I'm not putting in the statement of the theorem. You have to do this for an odd prime p, and you have to assume that p is unramified in F. So there's some conditions on which primes for which this is true. But under some odd conditions, we get that the conjectural exact formula holds. Okay, so now let me say in more detail about this conjectural exact formula. Okay, so I can't say exactly what the formula is. That would be a whole lecture by itself. But I can, in a sort of a simple setting, give you the shape of the formula. So let's assume that p is an inert prime. So the rational prime p generates a prime ideal of F. And then the shape of the conjecture is that the Brumer-Stark unit is a specific power of p times the multiplicative integral in the sense of Darmon. Okay, so this is just a sort of an integral that where you, instead of taking Riemann sums, you take Riemann products. Other than that, the definition of integration is exactly what you're used to. It's a limit of Riemann products. And that's what the x through the integral sign denotes, that you're taking products instead of sums. And you're integrating over the space OP star. So OP is just the p-adic completion of the ring of integers O. And you take the units in that ring, and we just integrate the function x. So x is the variable in OP star, and it's an integral with respect to a measure. And so the interesting part of this is not the function that you're integrating, it's the measure that you're integrating with respect to. So a certain very special measure on the space OP star, which is defined using the Eisenstein cocycle. And the Eisenstein cocycle has a very rich history, and there's a very large literature on it, especially a very large recent literature. This is a topic of a lot of current research. And so there's actually too many names to name, and I'll just mention some names involved in the definition of the cocycle. There's different versions of the cocycle. So there's Shintani's method, and that was picked up on by Hill and I should say mention David Solomon first, and then also by Hill. And then there's another method due to Robert Check, and also a method, an original method using the topological polylogarithm due to Bailenson, Kings, and Levin. And some of my work joint with Pierre Charlois, Matt Greenberg, and Michael Spiess, who I mentioned in the previous slide, also sort of builds on these works of Shintani and Check, and gives approaches and integrality properties of this Eisenstein cocycle. So you use this cocycle to make a measure, and then you integrate the function x on this measure, you multiply it by a simple power of p, and my conjecture is that gives you the Brumer-Stark unit. Okay, and what's amazing is that integral formula is really computable. So it's explicitly computable. And so I had some students, Max Fleischer and Nijia Liu, here at Duke, code this integral and compute it, and just come up with some really nice examples. So if you take sort of Q adjoining the square root of 305, and I chose that example because its narrow Hilbert class field has a degree 4. So you get a nice degree 4 polynomial. It's not something simple and quadratic. And you choose the prime p equals 3. And you can compute this integral. And there's a formula not just for U, but for all of its conjugates under Galois. So here there's 4 conjugates. This is a degree 4 extension. And you can write down all of the 4 integrals that you get. You get these p-adic numbers. And you take the elementary symmetric functions of these p-adic numbers. And then you ask the computer, what integers or half integers are they close to? And it tells you, okay, 9 or 345. And you do it to 100 p-adic digits. So it's 3 to the 100, some big number, and it has some complicated integrals. And all of a sudden you take their symmetric polynomials and you get a number like 9, which is 1 digit. Then you've pretty much gotten the right thing. So then you recognize very easily this polynomial. And so you can see that I never gave myself the answer. I never told myself or told the computer, what is the Hilbert class field of Q adjoin root 305? We just gave it some integrals and computed them, and then the computer spit out this polynomial. And then after the fact, you can check that this polynomial splits and generates a abelian extension of Q adjoin root 305 of degree 4, and that the Galois group of that extension is abelian, and that extension is unramified at all finite primes. So that is the Hilbert class field. So it's correct. You kind of verify it in this case. And then you can here's a larger example, 473 square root actually has a degree 6 extension. We took p equals 5. And you get these slightly larger numbers, but you can check at the end of the day, the splitting field of this polynomial is a Galois extension with Galois group z mod 6. And the splitting field of this polynomial is unramified at all finite primes. So you've gotten the Hilbert class field, narrow Hilbert class field of this extension. So this is, to us, in the spirit of Hilbert's 12th problem, we're writing down integrals that generate these class fields, right? And so in this direction, what is the concrete statement you can make? The concrete statement you can make is that you really are getting the maximal abelian extension if you take all of these Brumer-Stark units. And this is actually relatively simple to prove. Oops, I want to go back, sorry. The statement is just that the theorem is that if I take all of these Brumer-Stark units for all my primes p and all abelian extensions, then in fact, those Brumer-Stark units generate the maximum abelian extension up to the addition of some square roots. You have to throw in some simple square roots. So the square root of elements whose signs generate all possible signs, then those together with your Brumer-Stark units generate the maximum abelian extension. So in that sense, we're solving the question of generating the maximum abelian extension of a totally real field using p-adic integrals. Okay, so I'm going to talk now about the proof of this conjecture. So the theorem that I stated earlier in this talk, and Mahesh stated in his talk, is that we can prove this conjecture. So we can prove that we're generating the maximum abelian extension via these p-adic integrals. Okay, and in the proof, what's going to be an essential part of the proof some refinements of this conjecture and of the Brumer-Stark conjecture using fitting ideals. So let me try to define fitting ideals, which was mentioned in the previous talk and which will play an important role in the remainder of this talk. So let R be a commutative ring and M a finitely presented R module. So being finitely presented just means that you have an exact sequence like this. So there's a surjection from R to the M to capital M, which says that M is finitely generated, and that there's so finitely many relations that tell you all the relations that you need between these generators. So that means that there's an exact sequence like this. R to the N goes to R to the M, goes to capital M. Okay. And the fitting ideal is defined to be the ideal of R generated by all M by M minors of the matrix representing this map, which sends your relations to the generator. So this map describing the relations, the map F, is represented by some matrix, okay? And if you take all M by M minors of that matrix, so take all M by N submatrices of this M by N matrix, and you take the determinants of all these M by M submatrices, then you get what's called the fitting ideal. And what's important about this definition is that ideal is not dependent on the particular presentation that you take. That is, if M is a finally presented module, you can imagine 2 different, 3 different, many different presentations of this module. So different N, different M's, different F's that sit inside of an exact sequence like this. But the fitting ideal is a well-defined ideal. It doesn't depend on which presentation you take. So that's the first property. And the second property, and this is actually easier to prove, is that the fitting ideal annihilates the module. Okay, so the fitting ideal annihilates, is contained in the annihilator of the module. So just to give you an example, I think it's good at this point to give an example. If your R is just Z, so you're talking about finitely generated abelian groups, right? So we know what these are. These are Z to the R cross a product of cyclic groups like Z to the Z mod NZ for various integers N, right? What is the fitting ideal as a Z module, such a thing? Well, if the rank is positive, then it's actually, the fitting ideal is just 0. Okay, so it becomes interesting when your finally generated Z module is actually just a finite abelian group. So it's a product of cyclic groups. So the product of Z mod N and I. So I think I can write this. So say R equals Z and M is the product of Z mod Ni Z. Okay, then, then the fitting ideal as a Z module of M is the product of the Ni. And I note that this actually works even if one of the Ni is 0, so I didn't need to take that out as a special case. So the fitting ideal is basically the product. Okay, so in other words, if M is finite, then this is just fitting ideal over Z of M is generated as an ideal by just the size of M. Okay. So this is the special case where your ring is just Z. Okay, it's a very special case. So in general, this fitting ideal is a notion of size. It's a nice notion of size of a module over arbitrary commutative ring of a finally presented module, but it's a refined version of size. It's more than in the case when your ring is not just Z, it tells you more than size in some way. And you can see in this case when R is Z that indeed this fitting ideal is contained in the annihilator. Of course, the size of a finite abelian group annihilates the abelian group, but it's not necessarily equal, right? Z mod 2 cross Z mod 2 has size 4, and of course it's annihilated by 4, but it's in fact annihilated by something smaller. It's annihilated by 2. So the annihilator can contain the fitting ideal properly. Right. Now, an important special case is if N is equal to M. So if you look back at my exact sequence here, I have R to the N going to R to the M. So if I have the same number of relations as generators, then we say that M is quadratically presented. And in that case, the fitting ideal is just determined by the determinant of that one matrix. So then that's an M by M matrix. There's only one submatrix, namely itself. And the fitting ideal is by definition just the determinant of that matrix. So that's a very nice and special case when you have a principal fitting ideal. Okay. So now let me give some refinements of the Brumer-Stark conjecture now that I've defined fitting ideals. So the first refinement is that, this was stated by Mahesh, which is that theta st pound, this hash just means you apply the inverting function on the group, viewing this as an element of the group ring. There's an, the pound gives you a Z linear map on Z bracket G. And so if you take the pound of this theta, which was our Stickelberger element made out of L functions, that is an element of the fitting ideal of the dual of the tech class group. Okay, and for and there's an even more refined conjecture, which says not that something is inside a fitting ideal, but actually an equality of fitting ideals, which is the fitting ideal of some module. So Mahesh mentioned the Selmer module. I'm mentioning some slightly different module called a Ritter-Weiss module, because it'll show up in my later discussion, which is a canonical transpose of that Selmer module. So I'm not going to define either of these, the Selmer module or the Nabla, okay? But just to say that there's some other module whose fitting ideal is actually equal to theta. And the fact that, Burns, Kurihara, and Sano had made a conjecture that had described such a module and conjecture that its fitting ideal is equal to theta is absolutely essential in our proof, and somehow quite remarkable. Sorry, I had to pause the recording for a second, but I'm back now. So we have this remarkable conjecture of Kurihara, Burns, and Sano that there's a canonical natural Galois module. It's some generalization or fancier version of the class group whose fitting ideal they conjecture to actually equal the Stickelberger element. And having something both where you have an equality conjecture and where you have a principal ideal both of those properties were essential in our proof. So it was kind of very fortuitous for us that this conjecture was there, because just proving the Brumer-Stark conjecture directly using these methods seems to be quite difficult, but proving an equality of principal ideals is something that's simpler via the methods that we have in mind. Okay, so again, I'm not going to say what this Ritter-Weiss module is. So it was, of course, defined by Ritter and Weiss initially, and then Mahesh and I gave a slight refinement where we introduced a smoothing set, which is denoted T here. This T is the set that Mahesh called just a single prime Q in his talk. I'm using slightly more general notation. We use an arbitrary set T. So what Burns, Kurihara, and Sano did is define a sort of a transpose of this called the Selmer group, but both of these show up in our work. In any case, I don't want to say what Nabla is, but just tell you that it sits inside a short exact sequence with a generalized class group on the left, and then a very simple module, basically the module generated by the places of your extension field H that live above the primes in your set S, the degree 0 subgroup of that. It's a very simple module, this X. Okay, but we're not really going to use that. What we're going to use is a theorem that Mahesh and I proved, which is that homomorphisms from this Ritter-Weiss module, Nabla, to some other module, N, to any other module N, are characterized by cohomology classes valued in N. And this is a very important result, because Ribot's method is about producing cohomology classes. So the result that you want at the end of the day, which is something about the fitting ideal of Nabla, you have to kind of relate that to cohomology somehow. And so this theorem allows us to do that, which is that cohomology detects surjective homomorphisms from N. Okay, so so the goal then becomes, if we want to get a surjection from Nabla to N, to just produce a cohomology class valued in N that satisfies certain properties. And why do we want to produce a surjection from nabla to some module n? Well, if you can produce a surjection from nabla to some module n, such that the fitting ideal of n is contained in the principal ideal generated by theta, then you automatically obtain, because of properties, functorial properties of fitting ideals, that the principal ideal of nabla is contained in theta. Okay, so this is a property of fitting ideals. If nabla surjects to n, then the fitting ideal of nabla is contained in the fitting ideal of n. So if the fitting ideal of n is contained in the ideal generated by theta, then the fitting ideal of nabla is contained in the fitting ideal of theta. So the summary of the discussion that I just made is that to prove an inclusion of the fitting ideal of nabla into theta, which is kind of half of what we want an equality, right? So if you can prove an inclusion, what you need to do, or what it suffices to do, is to construct some module n, a Galois cohomology class valued in n, satisfying certain local conditions, such that the fitting ideal of n is contained in theta. And so now kind of nabla has been erased from the picture, and you can construct any n you want that in a cohomology class satisfying certain local conditions, and then in a fitting ideal inclusion. Okay, so nabla now has been replaced by this cohomology class that you are now tasked to construct. And an important observation, which Mahesh said is a standard thing in Iwasawa theory, but it's actually quite subtle in this application, is that it suffices to prove an inclusion in order to get an equality. That is, if you have an inclusion of the fitting ideal of n into the principal ideal generated by theta, then you can prove that inclusion actually is an equality. And in some sense, this is appeal to the size. So somehow, if one ideal is contained in the other, and the size of the quotients of the ring by these ideals is the same, then the ideals actually have to be equal. That's the basic idea behind it. Okay. Okay, so now to describe the proof of this, I'm going to now get into Ribot's method. So I wanted to summarize Ribot's method first with a schematic diagram. So we want to connect L functions to class groups, or to this nabla. And the way that we're going to do that is we're going to first realize that L functions are constant terms of Eisenstein series. Now, Eisenstein series are certain modular forms, and from Eisenstein series, we can produce cusp forms. And if I take cusp forms, and using cusp forms, I can deduce from this certain Galois representations. So cusp forms have Galois representations associated to them. And this is important because associated to Galois representations, we can make Galois cohomology classes. And Galois cohomology classes, we can show, are related to class groups. And this last link is what I just described, that the Galois cohomology classes give us homomorphisms from nabla. Once I get information on the fitting ideal of nabla, then I can from that deduce something about the fitting ideal of the class group, because the dual of the class group is a quotient of nabla. Or it's a quotient of the transpose of nabla, which is the Selmer group. Okay, so, all right, so now let me get into this initial part of this construction. So we're going to start with the space of Hilbert modular forms over the field F of weight K with Fourier coefficients in this group ring, ZP bracket G. And we take this, the subspace of those modular forms such that there's a compatibility involved. That is, there's an action of diamond operator sort of indexed by this group G, and you want to know that the diamond operator associated to an element in the group G just acts by multiplication in that group ring by the same element G. So another way of saying it is that every character of G you can apply to ZP bracket G and get something that's basically ZP valued or CP valued. And you want to know that that sort of classical Fourier expansion is the Fourier expansion of a modular form of Nebin type is chi. It's an equivalent definition to what I said in terms of diamond operators. Okay, so an example of this is the Eisenstein series. Okay, so an Eisenstein series is the simplest modular forms are modular forms that you can actually write down. And we have an explicit Fourier expansion where the reason that this Eisenstein series shows up, this is the weight one Eisenstein series, is that its constant term is exactly the Stickelberger element that we're interested in proving results about. Okay, and the other Fourier coefficients, so usually you get kind of the norm of A to the k minus 1, or in weight k, times chi of A, where chi is a character and you're getting an Eisenstein series of character chi. Now we're doing this in a group ring fashion, and it's weight 1, so k minus 1 is 0, so that term doesn't show up. And chi of A is just kind of replaced by A itself, or the Frobenius of A. And so that's the sort of Q expansion of this Eisenstein series. Now, let's remark, and there's always exceptions. In level 1, there is an exception. This formula is slightly off. Okay. Now, the idea is you make a cusp form out of this Eisenstein series. So this is getting a little bit complicated now. So please bear with me. It's actually simpler than it looks. So the point is you have this Eisenstein series, but the problem is it's not a cusp form because it has a constant term. It has a constant term theta. So to make it a cusp form, meaning you want the constant term to be 0, you want to subtract off its constant term, theta over 2 to the d, times some other modular form that has constant term 1. Now, unfortunately, it's hard to prove that you can write down a form of weight 1 that has constant term 1. But you can prove that there's a form of high enough weight that has constant term 1. So let's call that hk minus 1, form of high enough weight with constant term 1. And so I subtract off just E1 minus theta times hk plus 1. Now that doesn't make sense because these live in different spaces. E1 has weight 1 and hk plus 1 is weight k plus 1. So what I want to do is multiply E1 by a form of weight k to get it into the same weight as hk plus 1. But I don't want to change E1 very much. So I want to prove that there's a form of weight k that's basically equal to 1 or congruent to 1 modulo a high power of p. Okay, so you want to form vk, which is congruent to 1 modulo high power of p. And how high a power of p do you need to take? Well, just take high enough such that theta divides it, because everything is going to be mod theta at the end of the day. So if it's congruent to 1 mod high power of p and theta divides p to the end, then that's good enough. Okay, so if you do that, then this cusp form basically modulo theta looks like E1, because vk is congruent to 1 mod p to the n, and p to the n is divisible by theta. So mod theta vk is just 1. So I get E1 of g times 1. And then mod theta, this goes away, okay? I'm working at p-adically away from p equals 2, so this is divisible by theta. And so this goes away. So you just get f is congruent to E1. So that's the essential starting point of Ribot's method, is to get a congruence between an Eisenstein series and a cusp form. And I should mention that the existence of this vk and hk plus 1 were proven by my postdoc, Jesse Silliman, generalizing results in the lambda-adic case to the group ring case that I'm using, results of Hida and Chai. Now, this is almost a cusp form. It has constant term at infinity equal to 0, but actually it's more complicated because there are other cusps on the Hilbert modular variety. It's not just one cusp infinity, there's many other cusps. And so you need to do something more fancy in order to get something that's actually cuspal, that has constant term 0 at all the cusps. And I won't say what that is, but at the end of the day, you still get a cusp form that's congruent to your Eisenstein series. Okay, and now we're kind of off to the races. We have a cusp form. Now, it's not quite an eigenform, so for the rest of the talk, I'll pretend it is an eigenform, just for simplicity. And when you have a cuspal eigenform, it has a Gauss representation associated to it. And because this cusp form is congruent to an Eisenstein series modulo theta, it means that the Gauss representation is reducible modulo theta, because the Eisenstein series has a reducible Gauss representation associated to it. When the forms are congruent, the representations are congruent. So F is reducible modulo theta. Now, reducible Gauss representations give rise to cohomology classes. So I can kind of say this in a kind of simple way, like if I have 1, 0, say some character chi, and then a star here, that's what a reducible Gauss representation looks like. Well, maybe chi1 and chi2 in generality. In our case, it's really 1 and chi for some character chi. The star is your cohomology class. If you write down the fact that this is a group representation and you remember how to multiply matrices, then the star basically satisfies the co-cycle condition. Another way to think about it is the star represents an extension of chi by 1. An extension, x1 and h1 are basically the same in the context of modules over a group ring. Okay, so the fact that the congruence is modulo theta means that this module, basically it's the module generated by the star. That's your n. It's the set of elements generated by the star. That's your n. You get a cohomology class valued in that module. And the fact that your congruence, in order to get it reducible as modulo n, turns out to, by general functorial properties of fitting ideal, imply that the fitting ideal of this module is contained in theta. Okay, so the fact that the congruence is modulo theta means that the fitting ideal is contained in theta. Okay, so now we're basically done. We have a cohomology class valued in some module n. It's whatever module is generated by this star. And we've shown that the fitting ideal is contained in theta. And that's exactly what I told you is enough to get a surjection from nabla and to show that the fitting ideal of nabla is contained in theta. Right, so that's kind of the conclusion of the proof, or the summary of the proof that I wanted to give, and the description of Rivet's method as applied to our theorems. Now I'm just going to conclude by just saying, what additional things do you need to do to get my p-adic integral formula? Well, we again use group ring valued modular forms. We show that my conjecture, or more precisely, an integral version of the Gross-Stark conjecture due to Gross, that Gross's conjecture is equivalent to some statement about fitting ideals of some generalized version of nabla. And then to prove that statement about the fitting ideal of nabla, we use, again, group ring valued modular forms and the proof of Brumer-Stark. And a new feature, in addition to this integral Gross-Stark conjecture, which shows up, is that to relate the integral Gross-Stark conjecture to my p-adic integral formula, we use this method of introducing auxiliary primes to our set S, which is often discussed or called horizontal Iwasawa theory, or the Taylor-Wiles method. So this is the method used by Taylor and Wiles in the proof of Fermat's last theorem. So this kind of idea of introducing auxiliary primes and moving in Galois in a horizontal direction rather than vertical towers, but getting more and more ramification at additional primes, that's due to Taylor and Wiles. And in fact, that idea shows up originally in work of Wiles alone in the proof of the Iwasawa main conjecture. That idea is used very strongly here. Okay, and that concludes my talk, and I'm very much looking forward to taking your questions and discussing these ideas and some ideas you may have very shortly. Thanks very much.